Hello everybody, this is Craig, and what we're looking at is the long-awaited video I promised a couple days ago. Oh, having some family issues with mom in the hospital, and you might hear a bird today. I'm bird sitting, which is, boy, is that an adventure. Anyway, this video, a couple of you asked, several of you have asked, how do you know when a problem is a permutation, when it's a combination, or when do you use the FCP, or when do you have one of those combination problems that you'll use a permutation or a combination within the FCP? Yeah, that's the challenge of these things. The math work isn't so bad. Well, let's dig in. Let's do some review first. First of all, what's a permutation? A permutation is a grouping where we have a distinct ordering, where ordering is important in those groups. For example, um, let's say I have three colors, red, blue, and green, and I was arranging them in my order of my favorite to my least favorite. And I really like red, I kind of like blue, and I don't like green. Well, if you asked me, is blue, green, and red a different permutation? In this situation, where I'm listing my favorites first, second, and third, I would say yes, these are two permutations. Red, blue, and green is one, and blue, green, red is another because order is important. Now, if I was simply drawing colored discs out of a hat or something, and they had colors red, blue, green, and yellow and orange and everything else, and I just said, oh, one time I drew, or I asked how many different groups could I make up, and I said one possible group is red, blue, green. Another one is blue, green, red. You might go, oh, Craig, those aren't two different groups. If you're just drawing colors, you're not looking for permutations. Order doesn't matter. Those are two different combinations. And you would be right. Okay, in this video I'm going to use the format that our text uses. We used to use a different format, and yeah, you've seen me do something like this, right? That permutation is P3, 2. That's another way to do it, but that was our last textbook, so you'll see me using this subscript form before, and I'll call it a permutation of 3 select 2. Well, I would have called it that for either way, but okay. Now, one thing I haven't talked about, maybe I haven't, I'm not sure, maybe I did in that other video, is that we cannot use our permutation formula in this format. Whether you calculate it by hand or whether you use a scientific calculator, you cannot use it when we have repetition. It will give you the wrong answer. So if you're doing a combination and there's going to be, whoopsie, you're going to have 4 different numbers in the, say it's a passcode or something. And let's see, if you could use the numbers 1 to 9, 1976 might be a good permutation. But if we allowed repetition, then you might want to say, okay, I want another 9 there. And that's fine, it's still a good combination, but you could not use this equation and say, okay, let's see, I'm going to calculate this as, let's see, permutation of 9 select 4. No, that's not equal to this because we are allowing repetition in this example. So, whoopsie. All right, so let's move on. There's another type of permutation I haven't talked about it, and this is when we have alike objects. And we have a formula for calculating it. I'll come back to this formula in just a minute, but I want to start out by looking at what we're talking about. The book had this problem. What if you have the word moon and you want to create 4-letter words using those 4 letters? And let's see. They're going to be permutations because order is important, and also we'll make the rule that you can have nonsense words like OOMN is not really a word, but we're going to say it is in this example. So what could we do? Well, we got these two O's, and that's the complication. M-O, M-O, and I'm going to label them now, O1 and O2. That permutation looks a lot like this permutation if you take the subscripts off. And actually, these two are not two different groupings. They're not two permutations. So what you will find is when you have these double letters or triple, or you might have two pairs of doubles and a triple, something like they had that Mississippi problem in the book, you won't find that your answer, let's see, normally if this was a permutation, we might say that the answer would be, we've got 4 and we're selecting 4. And let's see, let me just double check. Pretty sure that, whoopsie, can't hit the right buttons. 4 permutation 4, yeah, pretty sure that was 24. But this is not going to make that many permutations. Why? It's because of those double letters. We have alike objects. So how do we use this calculation? Well, first of all, the k's are the different objects that we have that may or may not be repeated. For example, m is going to be k1, and it's equal to 1 because there's only one m. We have O's, that's going to be our K2. And we have two O's, so K2 is going to be equal to 2. And we have just one N, and will be our K3 equal to 1. Now also note that this says if we sum those K values up, we get N. So let's do it. 2 plus 1, we've got N equals 4 when we sum those up. Now we're ready to calculate how many permutations we actually have. And let's see, we have n factorial, which is 4 factorial, divided by k1 factorial, that's 1 factorial, times 2 factorial, times, whoopsie, not 3 factorial, is it? No, no, no. We have another 1 factorial. Now let's see, 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12 times 2 is 24. We know these 1 factorials equal 1. We know 2 factorial equals 2. So we're going to have a 2 in the denominator. How many permutations do we really have when we have like objects? Well, in this example, we had 12, not 24, 12. It's just a fluke that it's just half of it. Don't look at that as anything special. That's just because we had, well, I guess, 2 single letters and 1 double, and every other example will have something else, and it won't be that 50%. Well, it may, but it may not. Okay, that's permutations with alike objects. Moving on, combinations. We know combinations are another way to group objects. And by the way, that's what we're searching for in every single one of these problems. How many ways can we group things? Sometimes we forget that, and it's important to keep that in mind. All right, we know that combinations are where they're similar to permutations, but order doesn't matter in this case. For example, I guess I went over a combination example earlier, but here's another one. We're choosing letters from, I don't know, the fishbowl. And we pull out ABC, and then the second time we pull out BAC. Are these two unique groupings? Well, they would be two permutations if order mattered, but order doesn't matter. We're simply just making groups by pulling letters out of a fishbowl. We've given no significance to it. We're just forming groups. And so these are the same combination. It would only be counted once when we're creating groups. All right, once again, going to use that format for writing combinations. Finally, the FCP, the fundamental counting principle. The fundamental counting principle deals with tasks, or sometimes, what do we say, events, a sequence of things that happen or ways we do things. All of those work. I like to use the word tasks. You'll see me use that one a lot. Yeah, and we have an equation for calculating how many ways tasks can be sequenced or put into different orders. If we have one task that can be done A number of ways, and a second one can be done B ways, and a third C ways, well, then the total number of ways that we can sequence doing these three things is going to be A times B times C. Again, the tricky part is not the math. It's knowing when we got to use the FCP. Okay, and we'll give some hints as we go through these problems. Let's see. Oh yeah, here's a new one for you, and this is an important one, and I'm going to show this today in some of the problems we do. When we have problems involving permutations, when we've determined that this is a permutation problem, we can use our permutation equation, and if we had 4 select 3, we might plug this into our calculator. Oops, I said 4 select 3. I didn't write it. There we go. But any problem that's a permutation, as long as repetition is not allowed, we can also solve that using the FCP. And so we actually have 2 ways to solve permutation problems, as long as they do not involve repetition. Okay, that's good to know. Let's see, 4 select 3. We have 4 tasks, and we have a choice of 3 objects. No, the other way around. We have 3 tasks. And when I write the FCP, I always use these underlines. I call them slots. Used to draw boxes, but got tired of all those lines. So the FPC says we're going to multiply these things together. And how many ways can we do the first one? Well, there's 4 choices, recall. So that would be, we would have 4 choices for the first object. Once we've used one of the 4, we only have 3 for the second. And then 2. 4 times 3 is 12, times 2 is 24. And this permutation of 4 select 3. Oh, got to turn the calculator on, Craig. Turns off a lot on me. Lo and behold, this one is also 24. Our next question says how many 4-letter words, either nonsense words or real words, can be formed from the word panicky if each letter cannot be repeated. Not be repeated. Permutation formula maybe, if it is a permutation problem. Let's check this out. We're building 4-letter words from the from the letters in the word panicky. Yeah, this is our main group. We got letters. P, A, N, I, C, K, and Y. There's our choices. And now we're going to build 4-letter words. Well, one of them is icky. Icky, is that a real word? Gosh, I doubt it. Not sure. But I know that your feelings about Math 109 and permutations certainly run the gamut of icky to things much worse than that, don't they? Yes, they do. This is a tough class. All right, so there's one word. What if I just turn the letters around? Y, K, C, I. There's another grouping. Well, let's see. We made a nonsense word this time, didn't we? Yikey. Almost sounds the same. But no, totally different word. It's a nonsense word. But is it different? It certainly is. Is it the same letters? Yes, it is. That makes it a permutation. Order was important. The order that we put these letters together made a difference. And so we have a permutation here. Let's see. This was part A. We got part B to do yet. So this is a permutation. And it's, let's see, 4, select 4. How many did we have? 1, 2, 3, 4, 5, 6, 7 letters. All right, there we go. Okay, let's see. We could also do this as an FCP problem because it's a permutation without repetition. We're selecting 4 letters. We have 4 tasks. We're going to multiply them together. Let's see, how many did we have? How many choices for the first letter? Well, we had 7 choices. But then after we used one, we only had 6 letters left, and then we only had 5, and then we had 4, and sure enough, multiply these together and you'll get the same thing as the permutation of 7 select 4. What about part B? It says we're going to allow repetition now. Well, now we can't use our permutation formula because we have repetition. Now we must use the FCP. We must use the FCP. We know we have tasks. We got 4 of them. And let's see. Well, how about the first letter? We can repeat letters. So we can have a word like K, 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 K if we want, or N, 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 A. Those would both work. But how many choices do I have for the first slot? Well, there's 7 of them. How many choices for the second slot? Well, we can use that letter that we used in the first slot, so we still have 7 choices. So on and so forth. There's our answer. It's 7 to the 4th power, which is going to be a lot more than the permutation 7 select 4. Oh, let's do this one. 7 permutation 4 is 840. And I'll just double check my work. 7 times 6 times 5 times 4. Sure enough, there's 840. How many is this one going to be? Oh, it's got to be in the thousands, I think. I hit 7, and then I hit my y to the x key, and then I hit 4, an equal sign, and we've got a lot. 2,401 of them. 2,401 groups we could make of the 7 letters in panicky as long as we allowed repetition. Our next problem states how many ways can you select 3 websites to look at from a list of 6? Okay. Come on, pen. There's my first website, my second, my third, my fourth, my fifth, and my sixth. There's my group, or my choices. Let's make groups. Let's see, I'm selecting 3. All right. Well, I'm going to start viewing this first one. Then I'm going to jump to the second one, and then I'm going to jump to the third. Yeah, okay, I took them in order. Is that a group of 3 from the 6? Sure is. What about if I turn my viewing order around? What if I start with the third one and go to the second one that was listed and finally the first? Is that another group of 3 websites? It is. But are these 2 unique groupings? Well, let's see. They look like they're 2 different permutations, right? If order matters, yes, they are 2 permutations. But does order matter? Let's think about this. It said you're selecting 3 websites to view. Did it say choose my favorite website first or go to the sports website first? No, it didn't say anything about ordering. It just said go to 3 websites. And so these are the same combination. This is a combination problem. And so let's see. We've got 6 sites we're looking. It is the combination of 6 select 3. It's that simple. Does ordering matter or not? It's a question I ask on every one of these. Problem 4. How many ways can a student pick 5 questions to answer on an exam containing 9 questions? 9 questions. 1, 2, 3, 4, 5. A bunch more makes 9. There we have our 9 questions. Let's make a group. Well, let's just say I took the first 5. Oh, again, I'm skipping the second question because this is first part A. 1, 2, 3, 4, 5. Okay, there's one group of questions. Did I select 5 of the 9? I sure did. Let's make another grouping. How about if I chose to do 5 first, and then 4, and then 3, and then 2, 1? Is it a legitimate group? Well, sure it is. Is it different than this group? Well, I chose them in a different order. And even if you think about me completing them, I completed them in a different order. But did it really matter which order I did them in? Let's see. It's a quiz. I have to pick 5 of them to answer out of the 9. And well, I picked the same 5. No, order doesn't matter. Again, it's a combination. So what's our answer? We had 9 choices and we selected 5. Okay, I made a mistake and I'm backing up. Although if I edit this properly, you won't even know it. Let's see. We're on this problem where we were looking at a student choosing 5 questions to answer on this exam. There were a total of 9 questions, and let's see. Yeah, I wrote out the answer now. There's 126 ways. These 2 were combinations. Still the same problems. So it's the same combination. Let's look at part B. Get my drawing tool up here and going. Part B. Okay, now it says we're going to do the same thing, but he must choose his 5 questions. He must answer the first and 9th questions. So we still have 9 questions, except this time we have to answer the 9th question and we have to answer the first question. Well, as it turns out, if we're forced to answer those 2, they really don't come into play. We can sort of ignore them. Yes, that's right. We have to answer those. The real question is, what do we do with the rest of them? That's the question. What do we do with these guys? Well, let's see. How many are there? There's 1, 2, 3, 4, 5. There's 7 questions. And let's see. We had to choose 5, and we're forced to already choose 1 and 9. That means we have 3 choices from among these 7 that are left. And that tells me something. That tells me, again, we're looking for combinations because we determined this is a combination problem. They're not permutations we're looking at. It tells me that we now have 7 to choose from, and we're choosing 3. There's our answer. Combination of 7, select 3. There are only 35 possible groupings now. One might be 1, 2, 3, 4, 9. One might be, let's see, would 1 be 9, 4, 3, 2, 1? Nope, that's the same combination as I just said. We'd have to mix things up a little bit. That's why there's a lot less of them.